welcome back. We will discuss on the other nature of the fatigue in this session. So you can see this is a diagram which illustrates the effect of surface stress riser on SN curve. You can see three types of notches. Okay, the first one is a groove is taken on the shaft. Okay, so the first groove is rounded off to a larger length, the second groove is rounded off to a smaller length, and third groove is rounded off sharply. So with the 3 mm radius, 6 mm radius and 7.5 mm radius. So the endurance limit decreases as the size of the stress riser decreases radius of the crack, which agrees with the increase in the concentrated stress at the crack radius increases. You can see this in the right hand side diagram. Okay, this is a diagram which is taken drawn between the reversed nominal stress with number of cycles to failure. You can see the first one 7.5 mm radius, 7.5 mm radius, where the radius of the crack is bigger, the stress concentration is less in this case. Okay, whereas in the 3 mm radius material, this 3 mm radius, the diagram is shown at the below. Okay, you can see the stress concentration more on this one. So the number of the stress since the stress concentration is more, the number of cycles to failure is very less in this case of the material. Okay, so there is a diagram in between, that is 6, where it is having a 6 mm radius. So the fatigue life or endurance limit of this one is lying between these two. Okay, the endurance limit is more in case of 7.5 mm radius material, whereas the endurance limit is very less in case of 3 mm radius material, whereas the endurance limit is lying in between these two. Okay, for the 6 mm radius material. Okay, so the sigma c, that is the crack stress or the fatigue crack stress, can be calculated by using this relation. Sigma c is equal to sigma n into 1 plus 2 root of a by r, where sigma n is the nominal stress and a is the crack length and the crack tip radius. That the crack length and the crack tip radius are mentioned as a and r respectively. Okay, so from this we can see that how the stress riser can reduce the endurance limit of the material. Okay, so you should avoid higher stress concentration. Okay, mostly if you are able, if you can reduce the sharp corner or edges, your fatigue life of the material will be more, right. So coming to the fatigue failure, that is fatigue failure cycles, we will see different types of stresses which are helpful in generating these kind of fatigue cycles. So there are types of stresses for fatigue test, which includes axial, flexural and torsion testing. Okay, for axial and tensile compression testing, for flexural bending test, there is some different stress, and torsional or twisting, there is a different types of stress. From these tests the following data are generated. So first we should know what is a mean stress. Mean stress is nothing but it is represented by means of sigma m. Sigma m is equal to sigma maximum stress plus sigma minimum stress divided by 2, whereas stress amplitude sigma a is equal to sigma max minus sigma minimum divided by 2, stress range is equal to sigma max minus sigma minimum, and stress ratio R can be defined as it's a ratio between sigma minimum divided by sigma maximum. So by conversion, the tensile stresses are positive and compression tests are generally taken as negative. Okay, you can see these are the fatigue failure cycles. Okay, so examples of stress cycles, where the first diagram A shows the stress in a compression and tension. Okay, second one is B, which shows there is a greater tensile strength than compressive stress, and 3, all of the stress is tensile in nature. You can see the 0, okay, the nominal line. Okay, so if we get a sinusoidal curve that such that the material is subjected to both tensile and compression. So you can see initially it starts with the compression. Okay, then it goes to the tensile side, once again compression side, tension side, like this, where sigma m is equal to 0. That is a mean stress. What is a mean stress? Just now we have seen mean stress is nothing but sigma max plus sigma minimum divided by 2. In this case mean stress is 0. Now we can see in the second diagram, okay, you can see the compression stress is very less, whereas the mean stress is shifted in the tensile side. Mean stress is shifted to the tensile stress. Okay, now this first diagram is entirely shifted above, okay, because the sigma m is shifted. Initially it was in the line, okay, 0 line, now it is shifted to some distance. So the material has larger compressive stress when compared to, larger tensile stress when compared to compressive stress. Okay, in the third case you can see the sigma minimum is drastically improved, okay, so that there is no compression stress, okay, all the stresses are tensile, in tensile mode, okay, right. So fatigue stress cycles can be classified into 3 types. One is completely reverse cycle, second one is repeated cycle, third one is irregular or random cycle of fatigue, okay. So you can see the first diagram, the left hand side diagram A, where similar to the previous case we have seen that the tensile stresses, the stresses both in compressive and the tensile side, okay, where sigma A is the distance between the maximum point, okay, in both A and B, okay, both tensile strength and the compressive stress 0, from 0 to this one, that is amplitude of stress, and the range of stress is done by sigma m minus sigma minimum, okay, divided by 2, that is the range of stress, okay. So now you can see the second diagram, okay, this is the normal stress strain cycle, that is A, the figure A represents the normal stress strain cycle, where we can see it in a form in the shaft, normal shaft, okay, right. So you can see the second diagram where the sigma m is shifted towards the tensile side, so there is no compressive stresses, okay, only the tensile, the stress is the positive mode, that is tensile mode. The third stress cycle is, you can see, that is a irregular or random stress cycles, where you can see these kind of irregular random stress cycles in the aircrafts, okay, which are subjected to gust and wind, okay, aircrafts, in aircrafts these kind of that is random stress cycle will takes place. Okay, so coming to the types of fatigue, there are 2 types of fatigues. One is high cycle fatigue and another one is low cycle fatigue. So for low stress levels, wherein deformations are totally elastic, longer life results. We have seen this till now, up to our understanding on fatigue. We have seen that at low stress level, the life of the material is longer. This is called high cycle fatigue, okay, high cycle fatigue. You can see this in the diagram, it is represent high cycle fatigue in the low stress region, okay, low stress region, okay, where number of cycles are higher, okay. At higher stress level, you can see low cycle, LCF, lower cycle fatigue, where the number of cycles to failure is very less. So high cycle fatigue is associated with fatigue lives greater than 10 power 4 to 10 power 7 cycles. So generally high cycle fatigue occurs above 10 power 4 cycles to 10 power 7 cycles. So the SN curve in the high cycle region is sometimes described by means of a equation called as a Baskin equation, which is represented by means of n sigma a power p is equal to c, where p and c are the empirical constants, okay. So like this we can find out the high cycle fatigue. So high cycle fatigue is nothing but it is characteristics at low stress at more number of cycles. So coming to the low cycle fatigue, okay, it is a relatively high load that produce not only elastic strain but also some plastic strain during each cycle. So consequently fatigue lives are relatively short at less than 10 power 4 to 10 power 5 cycles. So at high stress level and low stress cycles, that is 10 power below 10 power 4 to 10 power 5 cycles, this low cycle fatigue is predominant. So this is the statistical nature of fatigue. Because the SN fatigue data is normally scattered, it should be therefore represented in a probability basis. So considerable number of specimens are used to obtain a statistical parameters. At sigma 1 is equal to 1% of the specimen would be expected to fail at N1 cycle, okay, N1 cycle. You can see the N1 cycle here, it is given on the left hand side of this diagram at sigma 1, because it is a higher stress level. So 50% of specimen would be expected to fail at N2 cycles, okay. You can see the N2 cycles, that is the number of cycles to failure is more, okay, where the probability of failure is taken in the range of p is equal to 0.50. For engineering purpose, it is sufficiently accurate to assume a logarithmic normal distribution of fatigue life in the region of probability of failure between 0.1 to 0.9. Right. So this is the effect of mean stress, stress range and stress intensity on the SN fatigue curve. Okay, so in the left hand side you can see the first diagram which illustrates the effect of sigma A, that is sigma A, or the effect of the mean stress on the fatigue strength. Okay, sigma A versus logarithmic number of cycles, it is taken here. You can see as the mean stress. See what happens, sigma m1 is at the top, sigma m4 is less. So here as the mean stress decreases, okay, the fatigue life increases. You can see the mean stress. Okay, if sigma m1 stress level is higher, whereas the number of cycles to failure is less, so fatigue strength is less. Sigma m2, you can see sigma m2, the stress is lower than sigma m1 but higher than m4, so the fatigue life is decreasing. Okay, so as the stress number of, say, as the stress level is decreased, the number of cycles or the fatigue strength is increased. Okay, that is what we can infer from this diagram. You can come to the middle diagram, where is the stress, range of stress. Okay, if you are taking the range of stress, okay, as the range of stress, you can see as the range of stress increases, right? So what happens, the fatigue strength decreases. Range of stress, you can see the arrow, stress range increases, the fatigue strength decreases. So R is equal to 0.3 has lower fatigue strength, whereas R is equal to -1 will have a higher fatigue strength. Okay, the third diagram, which is on the extreme right hand side, you can see is a diagram which with the effect of stress intensity. You can see the stress intensity is calculated by K is equal to sigma I divided by sigma local divided by sigma applied stress. Okay, you can see as the stress intensity increases, the fatigue strength decreases. You can see fatigue strength decreases, right? K1 is equal to 1. Okay, K1 is equal to 1.5. You can see the difference between these two. Okay, right. So the Goodman diagrams also shows the variations of the limited range of stress or mean stress. As the mean stress becomes more tensile, the allowable range of stress is reduced. Okay, at the tensile strength sigma u, the stress range is 0. That is what we can infer from this Goodman diagram. The other diagram is Haig-Soderberg diagram. Okay, Haig-Soderberg diagram is a plot of alternative stress sigma A and mean stress sigma m. So the Goodman relationship is expressed by sigma A is equal to sigma c into 1 minus sigma m by sigma u power x. Okay, so where x is equal to 1 for Goodman lines. Okay, for the Goodman equation to takes place, x should be equal to 1. For x is equal to 2, we can go for Gebber's formula, where sigma e is equal to fatigue limit for completely reversed cycle. If the design is based on the yield strength sigma naught, then the sigma u is replaced by sigma naught in this equation. Okay, so this is a small example. 4340 steel bar is subjected to a fluctuating axial load that varies from a maximum of 330 kilonewton to a minimum of 110 kilonewton compression. The mechanical properties of the steel are given as sigma u is equal to 1090 megapascal, sigma naught is equal to 1010 megapascal, and sigma e is equal to 510 megapascal. Determine the bar diameter to give infinite fatigue life based on a safety factor of 2.5. So we have to calculate the cylindrical, assume that the cylindrical cross section of the bar is equal to A. The variation of the stress can be calculated by means of these formulas. Okay, sigma m max is equal to 0.330 by A megapascal. Like that we have to calculate sigma minimum, sigma mean, and sigma A. After calculating all these values, we can just incorporate this in the Goodman's equation, where sigma A is equal to sigma E into 1 minus sigma m divided by sigma n. So if you apply that values, we can find out the diameter. Okay, we can get the area. A is equal to 1179 mm square. From that we can calculate the diameter. Okay, since it is a cylindrical cross section, area is equal to pi by 4 d square. Right. So fatigue fatigue failures, as the mean stress increases, the stress amplitude must decrease in order of the material to withstand the applied stress. This is summarized by the Goodman's relationship, what we have discussed in the previous slide. Okay, then coming to the cyclic stress strain curve, a cyclic stress strain controlled fatigue occurs, and the strain amplitude is held constant during cycling. It is found in thermal cycling, where a component expands and contracts in response to fluctuation in the operating temperature or in a reverse bending between fixed displacement. During the initial loading, the stress strain curve is from OA to B. Okay, So it will follow a opposite range when the load is removed. That is called, this effect is called as a Bossinger effect. Okay, so you can see the yielding begins on unloading in compression at a lower stress due to Bossinger effect. A hysteresis loop develops in reloading when it dimensions of width del epsilon and height del sigma. So the total strain range del E consists of the elastic strain component plus plastic strain component. So stress strain loop is calculated in the form of sigma epsilon is equal to sigma E plus del sigma P. Okay, del epsilon P. What is the meaning of this? Means there is a small amount of both elastic strain and plastic strain takes place, because elastic limit is recoverable. Okay, elastic limit is recoverable. Okay, when the load is applied on the material and it is removing the load, it will regain its into original position. But plastic strain, okay, it is a permanent strain. Okay, so that only it takes a reverse direction. Okay, it forms a hysteresis loop. Okay, so from this we can see we can find that the failure, that is the deformation of the material, is both elastic and plastic deformation. Okay, so coming to the structural features of fatigue, already we have discussed the fatigue process can be divided into various processes: crack initiation, slip band crack growth, crack growth on plane of high tensile strength, and ultimate tensile fracture. So we can classify into various stages: stage 1, stage 2 and stage 3. Crack initiation, it's the earliest development of fatigue damage. It can be removed by suitable thermal annealing. Slip band crack growth, the deepening of the initial crack on the plane of the highest stress. And third one is crack growth on planes of high tensile strength, growth of the well defined crack in direction normal to the maximum tensile strength. And the ultimate ductile fracture occurs when the crack reaches sufficient length so that the remaining cross section cannot support the applied load. So first stage is initiation of the fatigue crack, which is called a slip band crack growth. Okay, we can call it as a Wood's concept. Okay, so you can see when we are shuffling a deck of cards, okay, you can see the cards will be moving, one half of the card will be moving in the direction of the applied force, another one is in the opposite direction. Okay, similarly you can see these intrusions and extrusion takes place in the material when it is subjected to fatigue failure. So when the cracks are normally initiated at the free surface, the slip lines are formed during the first few thousand cycles of stress. Then the back and forth slip movements of the fatigue could build up notches or ridges at the surface, act as a stress riser which initiate the crack because of this continuous slip movements. Okay, you can see what is slip. Slip is nothing but the movement of the dislocation, okay, which is permanent. Okay, it's a plastic stage of a plastic deformation. Okay, it cannot be recoverable. In stage 1, the fatigue crack tends to propagate initially along the slip planes, extrusion and intrusion of persistent slip bands, and the later takes direction normal to the maximum tensile stress. So the crack propagation rate in the stage 1 model for fatigue initiation is generally very low. So the initiation of the crack length grows very slowly. Okay, the fatigue crack initiation is very slow. Okay, because the material will starts to strain harden. Okay, it will release its energy to oppose the external factors. Okay, so this because of this release in energy, the atoms are intact with each other. Okay, which oppose the crack to grow. Okay, that's why this crack initiation is very low. Okay, right, you can see the stage 2, it is called as stable crack growth. Okay, stage 2 fatigue crack. So plastic blunting, this is the process called as a plastic blunting. Okay, so since it is subjected to both tensile and compressive load, okay, initially the crack starts to build. Okay, so due to number of cycles, the sharp corner starts to, during tension it expands, during compression it gets sharpened, during tension it expands, compression it gets sharpened. Okay, and grow like this one. You can see this one, crack closed initially, and during the tensile strength the crack opens, then crack at maximum load. Okay, so crack closing, like that it goes on increasing. So crack tip blunting occurs during tensile load at 45 degree, and crack grows longer by plastic shearing. So the compression load reverses the slip direction at the end of the zones, crushing the surface to form a resharpened crack stress. Okay, so coming to the stage 2, that is fatigue propagation. Okay, So it is characterized by means of a dA by dN curve, that is called as a Paris regime. Okay, dA by dN is equal to A into del K power M. For design against a fatigue failure, fracture mechanics is used to monitor the fatigue crack growth rate in the Paris regime. So when the fatigue crack growth rate dA by dN varies with stress intensity factor range del K, which is a function of stress range del sigma and the crack length A. So del K is nothing but the stress intensity factor range. Okay, del K is equal to K max minus K minimum. Okay, or can be, can write like this one, sigma del K is equal to sigma max into root of pi A minus sigma min into root of pi A. So a log scale plot gives Paris exponent M as the slope. Okay, we have to draw a triangle at the center, that is the crack propagation road. From there we can find out this slope M and the other parameters required to calculate the dA by dN. Okay, so you can see this one, that's what I told you, we have to draw a triangle here. You can calculate the slope M. For design against fatigue failure, fracture mechanics is utilized. Okay, so the first stage, you can see the stage 1, non-propagating fatigue cracks. Non-propagating, the propagation rate is very slow. Okay, they won't propagate fast or slow. The second stage, you can see large influence of certain combination of environment, mean stresses and frequency. Okay, so the drastic rate. Okay, and finally the material is see static mode of behavior, cleavage or intergranular dimples, large influence of microstructure, mean stress in thickness, little influence on the environment. At the final stage, stage 3, the material will starts to break. Okay, so Paris law, there is another law, we call it as a Paris law, which is used for finding out the behavior at the stage 2. dA by dN is equal to C into del K power N. Okay, this is the Paris law behavior which can be calculated. Okay, in this stage 2 of fatigue crack, where sigma K is high, the cracks grow in a rapid and unstable manner until fracture occurs. Okay, right. The next damage model is called as a minor rule. Okay, and a cumulative damage model. It is expressed in the terms of sigma is equal to I is equal to 1 to K N1 divided by small n1 divided by capital N1, that is equal to D, where Ni or N1 is the number of cycles accumulated as stress Si, D is the fraction of life consumed by exposure to cycle at different stress levels, and the above equation can be thought of accessing the proportion of life consumed at each stress level and then adding the proportions for all other levels together. Okay, right. Now coming to the factors influencing fatigue properties, these are the various factors like stress concentration, size effect, surface effects, combined stresses, cumulative fatigue damage and sequence effect, metallurgical variations, corrosion and temperature. These are the various several factors influencing the fatigue properties. So this is the effect of stress concentration. Okay, stress concentration, already we have discussed all these things in our previous slides. Okay, we should avoid the stress rises from machining and fabrication process. Okay, as the stress rises increases, the fatigue strength decreases. That's what we have inferred from the previous understanding. So size effect, so fatigue properties better in small size specimens. Okay, fatigue properties are better in small size specimen. The problem is the machine cannot accommodate larger specimen. So larger specimen increases surface area subjected to cyclic load, higher possibility to find defects on the surface, and decrease the stress gradient and increases the volume of the material which is highly stressed. Okay, so it is usually impossible to duplicate the same stress concentration, stress gradient in a small size laboratory specimen. What is the solution is this? You use statistical approach. Okay, approximation, that is variable statistics. So the fatigue properties are very sensitive to surface condition. So fatigue initiation normally starts at the surface, since the maximum stress is at the surface. The factors which affect the surface of a fatigue specimen can be roughly divided into 3 categories: surface roughness, changes in surface property, and surface residual stresses. Now coming to the effect of combined stresses on fatigue. So few data have been made on the fatigue test with different combination of type of stresses. So ductile metal under combined bending and torsion fatigue follow a distortion energy, that is von Mises principle, whereas the brittle material follows the Tresca yield criterion, maximum principal stress theory. Okay, science have proposed expression for low strain and high strain This can be the both von Mises and the Tresca can be obtained from using these kind of equations. So effect of metallurgical variations of fatigue. So fatigue ratio can be, already we know that fatigue ratio can be calculated by means of a fatigue strength and tensile strength. It is the ratio between the fatigue strength and the tensile strength. As the tensile strength increases, the fatigue strength increases. So fatigue properties normally greatly improved by changing the design or reducing the stress concentration, introducing compressive stress on the surface. So few attempts have paid on improving material structure to improve fatigue properties, but it is still important. So fatigue property is frequently correlated with tensile properties. So you can see the fatigue strength improvement by controlling metallurgical variables by means of a strengthening mechanism. Okay, strengthening mechanism, you know what is a strengthening mechanism, we have discussed the strengthening mechanisms. Okay, so when we are creating a barrier in between the movement of the dislocation, the strength of the material can be included. Okay, so grain boundary strengthening, fiber strengthening, second phase strengthening and cold working are the various methods of increasing the strength of the specimen. Okay, so effect of corrosion on fatigue, you can see fatigue corrosion occurs when the material is subjected to cyclic stress in a corrosive conditions. So corrosion attack provides pitting on the metal surface, which pit acts as a notches, okay, which increases the fatigue strength. So chemical attack generally accelerates the rate of crack propagation. Okay, stress corrosion failure. So stress corrosion happens when the material reacts with a corrosive chemical in our environment. A good example is salt on the roads reacting with this steel in cars, causing reduced lifetime of the car's components such as its frame and suspension system. Another example is that a salt in the ocean reacting with the boats and their moorings, where the corrosion reduces the life of the engine, which is cooled by a salt water, and the structural integrity of the boat, which is geoparadized in salt water, sits in a hull or around the drive shaft. Okay, so with this we are completing the fatigue. Thank you for your patient listening. Thank you.